Okay, so last time we had we were calculating algorithmic complexity, and I'm gonna actually try my best to finish it today. Can you hear me now?
Yes.
Okay. Okay, you can see my screen. Hopefully the recording's still on. Okay, good. I don't know, just I pressed the power button when the thing went to sleep by mistake. Okay, so again, the last time we had we were talking about algorithmic analysis, and today we will continue. So so let's see. I think last time we saw a logarithmic growth. So let me just really quick here. So the last time, yeah, we had this log base 2 thing going on. And yeah, so right now we can actually continue with the examples here. Now, when we had this for loop, so just to reiterate this, so when you had a for loop for I equals to 0 and I is less than, or actually, I think it should have been, well, yeah, why not? And then we say I times equals 2, okay? And then your code goes here. So what happened was we knew that I will actually keep like running for 2 to the power of x or 2 to the power of k, let it be so, okay? Because this is actually like being multiplied, like this is actually just being raised to the power of 2 every time. So the first one is 2, the second is 4, then 8, then 16, and so on and so forth, right? So we have this logarithmic growth, and then we said that this will be actually, or can be rewritten as log base 2 of n, right? So this is like the runtime for that. There's also one more important thing I also wanted to mention here is that if in case you got like a weird number, not a weird number, but rather something like, imagine that you have a logarithmic function like this, for example, repeats, let's say for 8 times. So to say log 8 is going to equal to 3. Okay. So when you actually like calculate the log for this guy, it's going to be, it can be written as log base 2 to the power of 3 equals to 3. Okay. And at the end of the day, when you actually convert this, it's going to go to log base 210 equals to approximately 3.2 or something like that. Now, the point of the story here is like it's not about the calculation. What I wanted to say here is, if, for example, when you are calculating a complexity and you run into such a number, for example, what will happen is that you need to actually seal it. So a ceiling is, so you have in the math, you have a ceiling and floor. So ceiling means you approximate to the highest, and floor you approximate to the lowest. So in this case, when we calculate complexities, we usually say, aha, this is actually was going to be log base 210 is going to equal to 4. So we always round to the highest, okay? So this is called ceiling. Okay, this is called floor. And in math, sorry? Mohammed, your mic is unmuted, dude. Unless you had a question. Okay. So this is going to be 3 if you actually floor it. All right. So this is actually one of the things I wanted to mention here regarding calculating complexities. Now, when you actually like get something like this, so right now this is with a multiplication. If we actually go ahead and we say for I equals to 0, I is less than, or sorry, let it be larger than or equals to 1, I divided equals by 2, and your code just goes here. What will happen is, like, if you try to run this, it's going to be I all the time divided by n, isn't it? So, but this is actually keeping doubling. So practically speaking, sorry, or n divided by 2. So practically speaking, what will happen is you're going to have not I divided by 10. It's going to be n divided by 2, just to be clear here. So if I actually run this, like if I start to analyze this, so the first run, this is going to be n divided by 2. And then the next run is going to be n divided by 2 to the power of 2, right? Because it's actually keeping, like, again, you are dividing by more and more numbers, or larger and larger number. And this will keep repeating.
Is only I equal to n, not equal to 0?
Yes. Yes. Okay. So thank you for notifying me. This is like, I went automatic. All right, thanks. So at the end of the day, it's going to be n divided by 2 to the power of k. And what will happen here is, because you are keeping dividing by 2, keeping divided by 2 all the time, and this will be actually approximated to, at the end of the day, also to a logarithmic function. So it's going to be log base 2n. Okay. The rundown for it, the proof for it, is going to be going something like this. N divided by 2 to the power of k, assuming that the stopping condition is equal to 1, because it's larger than or equal to 1. So let's assume that this is the stopping condition. If you would by actually dividing on the two sides, or multiplying by the two sides with 2 to the power of k, you're going to end up with 2 equals to 2 to the power of k, right? And then this will be approximated again to k equals to log base 2 of n. Okay. So when you look at this, whenever you multiply like so, or you divide like so, you're actually going into this logarithmic realm. It's very important to understand that this I, if you look at it as an indexer, okay, that thing will never index every element in the array. So for example, like, it will actually keep skipping, and it will keep incrementally skipping. So it will reach the end of the array much faster than you are reaching the end of the array while iterating on each one of them. So logarithmic functions are way faster than a linear function. Okay. So if you draw this, this is linear, this is logarithmic, right? So this is how it will actually like pan out. It will maybe, okay, maybe the slope will be even a little bit less, but you get the idea. All right. Okay, but let us actually talk about, let's actually throw a curveball here. Let's look at another one. So if I actually give you something like 4i equals to 0, and I times I is less than n, I plus plus. Okay. And then your code goes here. how are we going to calculate the complexity of this thing? And this is actually even simpler than the one above it, by the way, if you think about it. Can somebody give me a guess? What would be the complexity of this for loop?
Is it I on the power of n or k?
Can you hear me now?
Yes.
All right. I don't know, for some reason the Wi-Fi just simply dropped apparently. I have no idea why. Okay, so just simply like the thing just got lost. Okay, let me just share my screen again. Apologies for the technical difficulties. Apparently, like things are going weird. So could somebody actually give me a guess for this? I was asking, does anybody give me a guess what would be the complexity of this thing? Did you hear the question before I got disconnected, or?
Yes, we did hear the question.
Okay. All right. So since no guesses, or educated guesses rather, what will happen here is, if you look at this is actually quite easy. The stopping condition is this guy. Okay. So if the stopping condition is this guy, so basically speaking, I squared, we can approximate it to actually equals to n as a stopping condition. We can approximate it like so. And actually, like, if you want to know what is the complexity of it, it's going to be just simply I square root of n. So this is basically speaking, this function is going to have an order of square root of n. Okay, so this is one like one way of calculating this. Now let's move on. So let's assume for a second that you have another for loop with I equals to 0, I is less than n, and I times equals 2, then you're going to have here p plus plus. And then you have another for loop. All this is enclosed in one single function, by the way. So you have another for loop, which is not nested, obviously. J equals to 1. J is less than P. J times equal 2. Okay? And your code goes here. Nobody cares about the code for now. Could you give me a guess what would be the time complexity for this guy? If you have a function like so, like that. So let me just draw a line right there, and we're going to call this func. And this is the opening braces. This is the closing braces. Can somebody give me a guess what would that be? What is the running time of this guy, at least? This one. Can somebody give me a guess?
Logarithm.
So logarithmic, okay, so this is log. What is the
2 of
time?
n.
So this is, excuse me?
Log 2 of n.
Oh, log base 2 of n. Okay, when I actually don't write the base, it's actually implied that it's log base 2. Even in books, they say that the log base 2 is implied in all books of algorithms, but okay. How much is this guy? Do we agree that this is logarithmic at least?
Yes.
Okay, so this is logarithmic, but how far it will run? It will run until p is actually running out, isn't it? Until p stops running. So this is basically log p. So if this function gets calculated, you're going to end up with a function of order of log p, or sorry, n, if we approximate it that way. Okay. So this is the calculation for it. Okay, let me throw you at you one more. And this is an actual complexity of an existing algorithm even. So we're going to have another for loop. I equals to 0. I is less than n. I plus plus. And then we have another for loop, which is going to be j equals to 1. J less than n. J times equal to. Okay. And then your code goes here. End of the story. Can somebody tell me what was going to be the time complexity for this one?
Log n, but everything is squared.
Mm.
The logarithm is squared.
No, it cannot be squared. It cannot be log squared because this one is not logarithmic, isn't it? So this is not logarithmic. This guy is logarithmic. So basically speaking, how long this guy is running?
N.
All right. How much is this guy is running? Also n times, isn't it? From the perspective of this loop. Now, if I actually grab another pen, how much is this guy running? From the perspective of this guy, just this loop is going to be log n, isn't it? But this is actually multiplied. And this guy also is running actually, like before I forget, so this guy is running also for n. And then from the perspective of this loop, this guy is also running for log n. For every time this actually increments, this will run logarithmically, right? So basically speaking, it's going to be O of n log n. This is actually the complexity of Quicksort, for example. But the code is not the same, but I mean, it's similar, but there's nothing, well, okay, I will not talk about the code right now, but the complexity of Quicksort, for example, is n log n in that way. Okay. So, does this make any sense? Is this clear?
Yes, yes.
All right. I'm actually gonna start getting a little bit faster here because I need to jump into asymptotic notations so we can actually so we don't lose time, because we need to carry on with the semester and other stuff so we can close the complexity theory chapter. So for the exam hackers there, we have a couple of patterns to recognize, right? So let me just write it down. Recognizable patterns. Okay. Oh, come on. There we go. So you have a for loop. Oh, I will not even write code in there. I'm just going to write headers. So equals to 0, I less than n, I plus plus. This is O of n. You have another one for I equals to 0, I is less than n, I plus equals 2, which is going to be n divided by 2, right? Which is approximately O of n, all right? Even though you are skipping by 2, you are skipping by 2. So for example, if you have an array of 10 elements, you're going to be running only over 5 elements. That's why it's n over 2, okay? Because you are just hopping on every other element. So we usually approximate it to O of n. Why? Because we are actually looking at the highest exponent. So we are taking the polynomial order. All right. If you actually see something like I equals to 0, or sorry, I is going here in this way case is going to be equal to 1, or sorry, n, and I is larger than, I has to stop at larger than 1. So you say I minus minus, it is also order of n. Okay, and then we saw the logarithmic. So for I equals to 1, I is less than n, I times equals to 2. Then we know that this is actually log n. So this is order of log n. And then the final one, just to make this material complete, equals to n. Then I is larger than 1. I divided equals by 2. And this is also going to have a logarithmic growth. Okay. So these are the patterns which you actually can recognize. And then if you have nested for loops right now, you know this is going to be n squared, and you're going to have, if you have, for example, if you have 2 nested loops, so if you have a for loop with whatever, and then another for loop with whatever nested beneath it. So these are nested. Then you're gonna have O of n squared. And if you have, I don't know, like 4 with whatever parameters you have, another 4 nested beneath it, and then another 4 nested beneath it, you are actually having O of n cubed and so on and so forth, right? It's going to be on n, O of n to the power of 4, and if you have more nested loops and so on and so forth. And this is assuming that there are no exit conditions and something like that. All right, so let's talk about analysis of if statements. So what happens if you have branching? What happens if you have if else? How can you actually solve that, right? So assuming that you have a function with an input n, whatever, right? And then you say, if n is larger than 5, then you do something. And then you have else. So this is right. Let's say this does some one line of code, which we don't care about. And then else, you're going to have a for loop of I equals to 0, and I is less than n, I plus plus, and then you do another operation, which we don't care that much about right now. Let's say it's a print or whatever. In this case, in this specific case, you're going to have two complexities, in fact. A complexity like what we call, like in some case, it will be actually O of 1. And this is because of this. So as long as n is larger than 5, it will take only just one operation to finish the job. However, if n is less than 5, it's going to take n times to finish the thing. So at the end of the day, you have a function that it has two different complexities. So in case you have branching in your code and you would like to know what's going to be the complexity of it, you say, aha, okay, there are two complexities for it. One, if a certain if statement was true, another one if if the else statement was true. And if you have a lot of nested else's, then you're gonna have as many complexities as there. And then right now, obviously, you can talk about the best case and the worst case. You can say, okay, how statistically speaking, how many times would I actually get n larger than 5, right? And how many times would I get n, let's say, equal or less than 5? And right now you start, thinking about this, and you can say, okay, the best case is going to be, for example, that because let's say 90% of the time we're going to get n always less than 5, then you're going to say, okay, it's going to be always like the best case, the worst case is going to be n, the best case is going to be of 1, because you always wish that n is going to be larger than 5, so you can execute this in only just in one time, right, of 1. But in any case, like if you have a complicated algorithm with if else's, then you need to just simply like, analyze every branch. In order just to make this also complete, so this is, let's say, so this is talking about branching. Branching with if else statements. And let me just take this out so it doesn't denote anything. There's also one more thing. Which I wanted to mention is the analysis of while loops. While loops are the same as for loops, right? Because even like we talked about this in programming 3 when we said that your for loops, when it's actually being taken by the compiler actually will lower it and will convert it into a while loop, which later on gets converted into a goto statement in assembly. But basically speaking, for loops are the same as while loops. You just simply like look at them in the same manner. And if you have nested while loops, then you have in fact like O of n squared, for example, if you have two nested while loops. While loop with a for loop also, it's going to be O of n squared, right? Depending, I mean, on the again, depending on the branching and stuff like that. So it's actually important to get to get this right. Like I'm just generally speaking, if you have a while loop that's running to n and a for loop running to n, and both of them are nested, then you're gonna get actually O of n squared. So this is one of the things I wanted to mention here. However, one thing I wanted to actually like to just for fun give you a small problem that a little bit different. Trying to get a straight line as possible desperately here. So let's say you're gonna have something like this. So while m doesn't equal to n, and this is one of the things which you need to walk through by hand, right? If m is larger than n, then you say m equals to m minus n, right? And then we have else, and then you say n equals to n minus m. Okay. Now, if I ask you to do a time complexity for this guy, this will be actually relatively difficult to hack. Okay. In fact, this is going to be, you're going to have a maximum and a minimum time, by the way, for this thing. Okay. And why is that? Because you have a branching happening here. Okay. So in order for you to figure this out, you need to plug in numbers and you need to run this by hand. But I mean, obviously, we are talking about exams here. You can just simply like look at this you can eyeball it if you want to. Like in production, you will have a little bit different kind of code that you can even eyeball it much easier. But let's say in the analysis, let's say that you are having such a thing in the exam and you need to solve it. So what you're going to do is you just simply say, aha, okay, let me plug in a couple of numbers. So here's m and here's n. If I plug in 6 and 3, what will happen is, aha, okay, will the for loop succeed? And say yes, because m doesn't equal to n. So is m is larger than n, then yes, then I will actually just simply subtract them. So it's going to be 3 and 3. So this is one execution. So this is execution. There you go. Let me count this. So exec. Okay. And then when the loop goes forward, then it says, okay, is m equals to n or doesn't equal to n? Then it says false because right now 3 and 3, m equals to n. So what you would do is just simply like stop. So basically speaking, no execution. So it is done. So your best case ever would be just O of 1. In fact, I mean, I'm talking about when the while loop executes, okay? So the best case, when the while loop executes, you're going to be O of 1. If I actually plug in m and n, which is going to be 5, let's say 5 and 5, no execution whatsoever, right? So this is useless input for me, but I know that this is actually what works. Let's say that I'm going to, in fact, plug in 18 and let's say 2. So this one will actually succeed, right? And then you're going to actually carry on with the numbers. So if this is actually succeed, then you can actually start subtracting m minus n because m so far is larger than n. So you're going to subtract in that for loop, you're going to keep subtracting like 2 by 2. So you're going to have, for example, 16 and then 2, right? Because you are actually in that execution. So this is an execution. This will execute again because m doesn't equal to n and it will always enter here. And this is going to be 14 and 2, then 12 and 2, then 10 and 2. Then you're going to actually go on so on and so forth. You can actually execute about like what, 9 times? Yeah, so 18 divided by 2 is going to be 9 times. Until you're going to get somewhere where it's going to be 2 and 2 in here. Okay. And this in total, you're going to get 9 executions. Okay. So practically speaking, whatever like in this case, it's almost like 16, like, or sorry, it's almost like 18 divided by 2 in our case, which we can actually approximate it to k or whatever k times, because I have no idea how many times this will appear. We can say it's actually be, in our case, divided by 2. So I don't care actually pretty much. This can be divided by 10. I really don't care about it that very much, but I care about what is the exponent here, right? And this is going to be actually exponent of 1, right? So practically speaking, this k is in fact, this is going to be like repeating, let's say, however, O of k or O of n, let's say, not this n, okay? This is not the n, the other n, or the O of k, practically speaking. We can approximate this to be O of k. So you happen to have two complexities, O of n or O of k in our case, and then O of 1, okay? In this while loop, for example. And this happens because of branching, okay? So this is actually important to get. So now that I actually have covered this, and right before the break, so I'm just gonna actually like give you, or you know what? How about actually I give you a break, because I need this to be in literally in one block, so I don't lose your attention right there. So how about I give you a break of 10 minutes? So right now it's 12:56. We return back at 12 and 5. Let it be. Oh, sorry, 1 and 5. 13, 5. If you have any questions, please feel free to post them on the in the chat. Okay, can you hear me? Hello?
Yes, yes, we can hear you.
Oh, okay. All right, so let's kind of go on. So far, there are a couple of types of functions, and you need to know their names. So you can like follow your fellow developers when they talk. Okay, so let's assume that you are working in a working environment, and you need to communicate something with your developers, and you're talking about certain function, how fast it actually grows or how fast it actually runs. So here are the namings of these functions. So if you have a function has an order or a polynomial order of 1, this is what we call a constant. Let me just write there, nice and yellow, types of functions. Okay, this is constant. Later on, if you actually see an order of log n, this is what we call a logarithmic function. Then if you have an O of n, this is what we call a linear function. O of n squared, this we call quadratic. Then you have O of n cubed, which is going to be cubic function. Then you have O of 2 to the power of n. That's what we also call exponential. If you see O of n to the power of n is also exponential. Okay. And if you see somebody talking about something like log squared, so it's going to be also called log squared. Okay, so these are the types of functions that you might see in the wild. Okay. So regardless of how far this guy runs, if it runs for 10,000 times or it runs for 2 times, it's still a constant function because we know it will run exactly for that amount and it will never change. So there's no variability here. So that's why we call it a constant time, right? Linear, this is right now how it grows. So it grows 1, 2, 3, 4, 5, 6, and so on and so forth. So it's actually simply like grows in a linear fashion, right? It doesn't, it scales with the input. So this is a very important note to mention here. Now let's actually talk about, I will actually go ahead and talk about asymptotic notations. But in order for me to talk about them, I need to order these guys. So I will take these guys and sort them. And I will sort them from the smallest to the largest. Okay? So I can actually, when I describe the asymptotic notation, now we get to the actual meat of the subject. So far, whenever we're talking about the order of a function, we talk about the polynomial order. Okay? So you have this O means a polynomial order. Okay? And now what scientists has done, or computer scientists rather, they actually started to categorize these functions. Okay, so they made in the asymptotic notation world, we have like about like 5 types of functions. 3 of them are important for us in this semester: big O, big omega, and big theta. There is a small omega. Sorry, there's a small omega and there's small o, but we will not look at them. So let's talk about that. So let's say here I'm just going to write in nice big letters asymptotic notations. Right now, actually, so far, like in the past, like 2 parts or something like that, we are actually, this is actually, even this will appear in interviews, by the way. So interview questions are full of these stuff, by the way, wherever you apply in some mission critical stuff. Okay, so if you go to the FANG, so Facebook, Alphabetica, I don't know, Microsoft, Google, and so on and so forth, they always ask about these asymptotic notations. Some of companies here in Bosnia, they also ask for it. So just be clear about this. So let's actually sort these numbers. Like, let me sort these guys out. So I'm going to have here O of 1. This is the smallest. This is like the fastest so far. O, then comes afterwards O of log n. Then comes afterwards O of square root of n. Then afterwards we have O of n. Then, by the way, these are polynomial order. So O stands for the order of the polynomial. Again, O of n log, log n. Then we have O of n squared. Then you can, or also O of n cubed. Then you can go as far as you go, like increment this thing to O of 2 to the power of n. Then you go for 3 to the power of n. And then you can go how many as you want until the maximum and the largest of them all, n to the power of n. Okay. So these are the functions, the polynomial orders that might appear in the wild, and they are being ordered from the smallest to the biggest. Okay. Now let's talk about the asymptotic notation. So I'm actually gonna just draw a line right there, like so, separator. Usually we use, just to document this for you guys, we use notations. For representing simple form of a function. Come on. Of a function, or let me just put it a little bit spaced out, or showing a class of a function. Okay. So this is what the asymptotic notations are for. You show a classifications of these functions. We just simply say what type they are, what category they are. So we have something which is called the big O, as I said. So it's written as O, similar to how we write the order. And this is why people are mixing it up everywhere on the internet. And actually on the internet, books, they never mix them up. Books are getting it always right. Just people on the internet are getting it wrong. Like 99% of the time. So this is called the big O, and it's written and pronounced as big O. Okay, this is what we call an upper bound function. Then we have big omega, which is actually called a lower bound function. And we'll learn in a minute what does that all mean. Then you have big theta, which we call average bound function. Okay. In practice, we usually look at this in practice. What I mean by that is on the average time, how long it will take for this thing to run. Because we never actually calculate, like, we never always look at the worst case, but we usually, in average, we are trying to hunt for this, right? Like to see what is going to be the average time. But basically speaking, I'm not saying we are usually looking at the theta. I'm saying the average, like, execution of a function, okay? So let's say like this. Usually we look at average let me write this down in a better way. Look at average execution of a function in practice. Because, I mean, you always say, what statistically speaking, how, like, will it be always running in the worst case scenario, right? So we usually say, like, we are trying to, like, look at the average execution time of a function. Okay, so let's actually define what a big O is. So when somebody goes on and he says, or she says, this function has a complexity big O of whatever, right? Now, big O is a classification of a function. So it is not this O, okay? Heck, even in some books, in order for them not to confuse people, and I've seen it actually, they write the polynomial order so the O has just this dash in the middle. So they don't say, not to confuse people with the big O, right? Because the O, the polynomial order, and the big O asymptotic notation are having the same letter, and everybody's confusing it for that specific reason. So let us actually write the definition. And by the way, these definitions are already also written in the white book. I think algorithm and data structure analysis in C, the white book with the wave thing. I forgot the authors, which I've given to you. That these definitions are already written in there, but I'm gonna just simply rewrite them there just as a reference, so we can talk about this. So big O. Okay. Let me just write this in a smaller h, like so. So big O. The definition of big O goes as follows. If you have a function t of n, we'll be having, so if you have a function t of n, will have a complexity, or will be a big O f of n as a function of an input. If there is, or if there are, rather, if there are positive constant if there are positive constants C, okay, and N naught or N0 or NO, whatever you would like to call it. So you have two constants. One of them is called C, one of them is called N0, such that T of N going to be less than or equal C times F of N. Oh, wait for the second break. It says when N is larger than or equal N naught. Usually, like when people are giving this stuff in the exams, by the way, like in the outside, like here we give you a code to calculate the complexity. Outside, we get actually, I mean, at least when I was a student and people outside, in the outside world, when they give you actually to calculate the complexity, they actually give you a function in this form, right? Of course, you extract it from this mathematical thing. You can actually look at it again as a code. You can transfer it into code, so you can see it better if you think like that. And then you can just simply say, aha, okay, this is actually a big O or a theta or a big omega and so on and so forth. Okay, so but what does this actually mean? Let's say for example that T of n equals to 2n plus 3. Okay, so by definition, I will actually just simply take this guy, substitute it here. Okay, so if I actually have 2n plus 3 less than or equals to, let's say for now, I'm just going to put here n, whatever input is going to be, right? So let's actually define this a little bit better. This is your T of n again, right? Because I already said that. I'll just simply took T of n, substituted with some example from my pocket, let's say, and just put it there. Okay. This, for example, if I put here, let's say 1, this is going to be your constant. This is your C. This is that constant. Okay. And this is your, in fact, f of n, the function which you are executing. Okay. So this is your code which you are executing. And this is your input which you are inputting into your function. Now, here's the thing. You can actually satisfy, you have to satisfy this condition. You have to satisfy this definition in order for this to become a big O. If you violate this condition, this is not a big O. Okay. So practically speaking, I can put here, I can do actually some calculations here. I can, for example, put here 1, and this will keep satisfying it because 2 times n plus 3 is, sorry, actually right now this is violating it. I have to put here, let's say 10n in order for it to work, right? I have to put it like maybe, I don't know how much right now. I have to like think about a number in order for it to be equal. So 2n plus 3 is going to equal to whatever on the other side here, and it will actually satisfy it. But the main thing here is, by definition, your function here has to have an execution time larger than or equals to, let's say, this n, whatever n is here. So if I even put here an n instead, okay, this condition is still actually being satisfied because of that equal bit, right? So your function, your f of n, your function which you are, your algorithm, has to be larger than or equal to that n, right? Meaning that if we look at the asymptotic notation, if we look at these functions, we can say that the range of big O that covers, so when scientists categorized it, they categorized it from O of n all the way until the end, right? So right now, this area, this part, this is big O. Based on that, that means, like, when you look at this, that means if I actually come in and say, if your function, that function, right, this function, if that function, f of n, equals to big O, not the polynomial, but the big O of n, and you can say it is a big O, then yes, it is correct. If you come again and you say f of n equals to big O of n squared, then it's also going to be correct, because this other side of the equation, you are actually satisfying. You are having here n squared, and your input is actually less than whatever your output is going to be, okay? Now, if I go here and I say f of n is big O of log n, this is utterly wrong. It is not big O, because by definition, big O only covers this side, this area from n downwards, okay? This is very, very important to get right. And this is where everybody makes a mistake about this. Everybody says big O of log n. Big O of log n is impossible, because by definition, big O, the asymptotic notation, does not cover that by definition. Polynomial order of log n, yes, but not big O. And we're going to see what is actually the definition of it in a minute. Does this make any sense? People?
Yes, yes.
Okay. Now let me carry on with the second one. Big omega. So this big omega. Now, big omega by definition, if you have a function t of n, if you have an input t of n, is going to be actually having, it's going to be like your function is going to be categorized under big omega of f of n. This guy will be categorized under that. If there are positive constants positive constant c and n naught n naught such that your t of n is larger than or equals to c times f of n. Now here's the interesting part. You see, it's just the opposite, right? That also means that if your function, if you have an input and you get an execution time less than the actual input, then this is actually a big omega. Okay, so if I input 10 numbers, which is n, and I get, let's say, n or less, right? Execution time units. So right now, for example, I input an array of 10, and then I got an execution time of, I don't know, 5 units. So right now, I actually halved my execution time, right? Right now, I didn't put in, if I put in, let's say, 20 elements of an array as an input, I get execution time of 10 over every input. So like if I actually loop over the array, like let's say I would like to sort an array. So you have sorting an element. You can sort an element. So if you actually push in, let's say 20 elements, and then in 10 loops, let's say it finishes sorting, instead of sorting each and other element, right? Like pulling it out like O of n or O of n squared, it actually just halved them. That means that actually it's a big omega function, right? So if I actually pull out the same example here, so 2 plus 3, or sorry, 2n as an input, plus 3, for example. If you have an input that looks like that, larger than or equals to 1 times n, this is your input t of n. This is your constant, obviously, and this is your function, f of n, okay? For all n is larger than or equals to 1, okay? As long as you satisfy that condition that your input is larger than your processing time, that this is actually a big omega function. That means that if you have a function, f of n, that is big omega of n, that is actually true because of this equality, right? If you have an f of n, big omega of log n, then this is also true because log n is less than n, right? However, if I actually say function has an execution time of big omega n squared, this is utterly wrong, right? This is also meaning that if we look up here, and I will grab another color, let's say yellow, your asymptotic notation of big omega covers this guy from O of n as well up until here. So this is your big omega. All right, so big omega. Because of that overlap, you can say big omega of n or big O of n. Both of them are correct because of the overlap. Okay. Now, let's talk about big theta. Now, big theta is, as you probably have guessed, it's actually in between. So this is going to be big, big theta. And this is big omega. And I'll just the line there. And squiggly here. And let's look at the big omega definition. So by definition, if you have an input T of n, it's going to be having an asymptotic notation f of n, or omega f of n, if there are sorry, let me actually I made the mistake here. Sorry, big theta, I'm apologizing. So it's going to be big theta f of n. All right, so it's going to be that. Well, actually, just in order, because we're going to have a lot of letters here, I'm just going to put here hn. It's going to be if, so it's going to be under that category if and only if okay, T of n is less than or equal big O of h of n. And T of n is larger than or equals to big omega h n for every constant C1, C2, and not such that and here's the formula for it. So C1 of h of n is less than or equal to T of n C2 h of n. Okay? That means that you are, practically speaking, the theta, big theta, is covering this guy. So this is your big theta right here. and big theta can be only O of n. So you cannot say the asymptotic notation of a function of O of n squared is going to be a big theta. It's impossible. By definition, not possible. Okay, so this is the important thing to note here. Okay. Finally, I just wanted to there are a couple of things. This is actually right now, this is the end of the complexity theory chapter, which has to be covered in order to make the subject more complete. Now, please understand that asymptotic notations, again, they are categories of functions. Understand that people are like this way of calculating complexity is not that super efficient. It's easy to give you an idea of the growth of a function based on an input. So if you have 10,000 customers, 1 million customers that you would like to sort in order to give them promotional coupons, for example, right? If you would like to do that, you need to apply a very efficient algorithm that doesn't, for example, hog the servers or kill the servers of them, like of a certain company, in order for it to finish executing and give the coupons away, right? So so what we usually do, like people are like looking at the asymptotic notation, then you're gonna get a rough idea of what is an execution time of an algorithm will be. However, the other more realistic kind of well, let's say more practical kind of calculating complexity is something which is called calculating amortized complexity. I'm just going to leave it here for further research. We are not going to cover it here, but I think it's a good thing that you know about. Maybe you're going to need it in the future. Something which is called this amortized complexity. Okay, and right there you actually calculate, like, for example, let's say if I'll actually give this example to in the classroom, just to give you an idea how different this asymptotic notations versus like calculating an amortized complexity. An amortized complexity has like four or five techniques, different techniques on how to calculate it. It's not a single technique like what I was showing to you in the asymptotic notation. Like there are several ways of doing this, and each one of them can be used for some use case, I think. But again, I will leave this for you to research. So let's say for example, I'm organizing an event and I'm asking you to like bring or like allocate. I need you to allocate some chairs for that event because I'm expecting a lot of people to come. So right now the question would be like, okay, can you please tell me, you will tell me like this, can you please tell me how many chairs do you need, right? And then I will say, okay, so there is a 5% chance, there's like a 5% chance that I'm gonna get 1,000 people. Okay, there's just 5% chance. Otherwise, in the other 95%, I'm gonna actually get, I don't know, maybe I'm gonna get 200. Okay. Now, of course, this is a kind of crazy example to have. We cannot have such a crazy difference, but in any case, you get the idea. And then you will go ahead and then you say, okay, I will try to allocate the chairs that you need. So if 5% chance you need to get 1,000 chairs, if you are using asymptotic notations, you're gonna say, this guy actually needs 1,000 chairs. I'm gonna actually allocate for that guy 1,000 chairs, right? Because based on the asymptotic notation, I got, for example, like let's say the worst case or the best case or whatever, like the worst case, let's say, you're gonna actually say, okay, what is the execution time of the function, right? Well, how many resources I need to allocate in order for this function to execute? Well, you say, okay, this is probably, this function has an order of, I don't know, O of n squared. Or in our case, in this example, this function having an order of 10,000 or 1,000 chairs right now. So you'll say, okay, I'm going to just go ahead and allocate 1,000 chairs, which is completely inefficient, just for a 5% chance that this will happen. So at the end of the day, you might allocate 200 or maybe 300 chairs, right? And this is the difference between amortized analysis or amortized complexity and this classical way of figuring out the asymptotic notation of a function using this technique, which I've shown you. Is that the amortized complexity you will actually get the asymptotic notations, like what is the category or what is the classification of a function, is a big O or a small O or a big theta or a small theta, or sorry, a small omega. You will get that also from the amortized complexity. However, the way it calculates it, it's a little bit more realistic. And at the end of the day, you will just simply say, okay, I'll allocate 200 or 300 shares. And this right now, which is more appropriate to do. However, for example, in production, let's say, in most cases, you will just simply utilize the classical way, unless you are working on a very mission critical stuff, which you really need to think about thoroughly before just spending the time and the money to implement. And right now you will just simply thinking like, okay, let's do the amortized complexity calculations. Let's make sure that we're really, really on the right track and we will not waste too much money and figure out how to execute or how to write a certain function. So yeah, I just wanted to mention to you like what is the difference, how different they are, and then you can just simply like go from there and just do your study. You will have these questions in the exams, by the way. Like you're gonna get a piece of code that you need to calculate the complexity for it. It is crucially that you understand how you do this. So at least like for the exam, you can actually pass it, and also for your future, like when you are doing, you're like trying to pass an interview, you're gonna need to know this. I'm actually like done here, so let me stop recording.